Hey, Chemistry 12, Mr. Lum again, and here is your latest worksheet for solubility chem. So anyways, this is going to be the video tutorial on how to do everything from this worksheet, and if you have any questions, refer to this. If you know everything and you had a question, jump ahead through this video. Anyways, you should be able to find this worksheet on Microsoft Teams. I'll post the answer key in case you just want to see the answers, but this will be the explanation of how I do everything. So first thing is that we should have our data booklet right here. So I'm going to kind of split screen this and kind of look at a few things at the same time right here and answer it this way. Okay, first question is that a solution which contains only one of the following, it contains either I minus, SO4 2 minus, or OH minus. And we don't know which one of these things it contains, so we test it using silver, iron, and strontium. And so we need to figure out which one it is. So for first off is that it forms a precipitate with silver. So if we look over here, we see that iodine and silver, it does form a precipitate. So that seems to check out. But it does not form a precipitate with iron. So iodine, that kind of makes sense for both of these ones. So it kind of is looking like it's going to be iodine, because iodine will only form a precipitate with Ag, but not with Fe or Sr. Fe and Sr would be under all others right here. If this was SO4 2 minus, it would form a precipitate with Ag, it would form a precipitate with Sr, okay, but not Fe. So it's not this one right here, because this would form a precipitate with these two right here, okay? So, and it's not OH. OH would form a precipitate with Ag and Fe, okay? And you can see that right down here. So the only one that it's true for is iodine. So we're going to write down iodine like that. Okay, next one. Forms a precipitate with these two, but not this one right here. So we've already kind of done this one in some sense, because these are the same things as these ones right here. Now, and we've already said forms precipitate with Ag and Fe. So forms a precipitate with Ag and Fe, but not Sr. That's going to be our hydroxide, our OH, which is down here. So forms a precipitate with Ag, which is part of all others, and Fe, which is also part of all others, but does not form a precipitate with Sr, soluble. So this one is going to be OH minus. It's not going to be CO3 because CO3 forms a precipitate with essentially everything, with the exception of alkali metals. And yeah. Okay, those are the first two done. Now we have this next one right here. A solution contains all of these different things inside of it. Okay, and what compounds and in the correct order do we add in order to take these things out? So again, we want to find a compound that takes out one of these, but does not take out the rest. Okay, so the first compound that I'm looking at right here is, let's take out this one right here. Okay, I can see over here that if we added something like, if we added NaCl, so if we added NaCl, again, Na is just a spectator, Cl is what's going to actually do the work for us and form a precipitate. It's not going to form a precipitate with Fe, Ca, or Be. It only forms a precipitate with Cu. So the net ionic equation for the precipitate reaction would be Cu plus Cl minus turns into Cu Cl. So then we would filter that off, and we've effectively eliminated all the copper 1 in there. Okay, now we only have these 3 left in there. Okay, so now we need to find something that forms a precipitate with one of these and not the other ones. So one of the things I'm looking at right now is I'm looking at SO4. Forms a precipitate with Ca, but does not form a precipitate with Be or Fe. So I'm going to go Na2 SO4. That forms a precipitate with, that goes SO4 2 minus, plus, and that combines with our Ca right here. So Ca2 plus, and that turns into CaSO4. Okay, so we've eliminated that one now. Now, technically, we could have had these ones switched. It doesn't matter which one of these ones that we started with, because we could have taken out the Ca first or this one first. So both would have been right in that one. Anyways, now we have only 2 things left in this solution. We have Fe and we have Be. So we need to find something that removes just one of these things right here. And I'm looking at one right now, and it looks like we see that sulfide won't remove Be, but will remove everything else. So in other words, it'll remove Fe3 plus. So if I put in, let's do this one quick. If I put in right up here, Na2S. Okay, again, Na is our spectator ion. And then what we're going to have is that'll take out the Fe plus the S2 minus. As we can see, S2 minus will not remove the Be, but it will remove the Fe, low solubility. So that'll go Fe swap and drop. Okay, so now we have removed this one right here effectively. Now we just need to find something that removes Be2 plus. Okay, and we could use hydroxide if we wanted to. That removes it very well. We could use PO4 if we wanted to, CO3 if we wanted to, or SO3 if we wanted to. So I'm just going to use hydroxide. So I'm going to write NaOH, and that is going to take Na as a spectator again, so OH minus plus Be2 plus, and that's going to form our precipitate, which is going to be BeOH2, like that. And technically I should have wrote solid like this for all of these ones to show that, hey, that's the precipitate that we're removing. So this is one answer that you could have for question number 3 right here. There could be many, many other answers. Okay, that was kind of review stuff from last time. This is kind of the new stuff that we're working on right here. So again, we need our table right here. We have this question right here. And I'm just going to kind of push this thing over a tiny bit to give us more writing room. And we have this one right here. It says a saturated solution of BaF2 has a fluoride concentration of 8.6 times 10 to the negative 3. At a certain temperature, calculate the Ksp at this temperature. Show all your steps in a logical manner. Correct use of sig figs and all that kind of stuff. Okay. So first off, I'm going to write out an expression. So it's going to be BaF2, and it's going to turn into Ba2 plus F minus. And I didn't really leave myself a lot of room, but if I'm balancing this equation, it should be technically, there should be a 2 in front of here, something like that. Okay. Now, it says that the concentration of the F minus in solution is 8.6 times 10 to the minus 3. I don't know why I said 3 minus there, but that's the way it goes. That's that concentration. Now, this concentration of F minus is going to be twice as much as the concentration of Ba2 plus. So this one's going to be, I just divide this by 2 to get the concentration of Ba. And so 8.6 divided by 2 is 4.3 times 10 to the minus 3 molarity. I don't know if you can see that little decimal place right there. Okay, so those are my concentrations of my ions in solution. Now, my Ksp expression is essentially the exact same thing as KEQ, but remember this is a solid because it has low solubility. I didn't bother writing it just because I guess I can. Aqueous, and only the aqueous is going to solution. Since this is a solid, it's products over reactants, but reactants is a solid, so it's just going to be the products. So it's just going to be the concentration of Ba2 plus times the concentration of F minus. But since there's that 2 in front, remember that gets that squared right there. Okay, now we don't know what Ksp is, but we do know what all these numbers are right here. So we can just plug in these numbers into here. So Ba is 4.3 times 10 to the minus 3. And I better do some brackets. And this one is 8.6 times 10 to the minus 3 squared. So Ksp equals, so I'm going to take my calculator, I'm going to go 8.6 times 10 to the minus 3, I'm going to write squared, times 4.3 times 10 to the minus 3 equals, and I get, these are 2 sig figs. My answer comes out to 3.18 times 10 to the, and my calculator fortunately doesn't give it to me in scientific notation. 1, 2, 3, 4, 5, 6, -7, like that. Now, Ksp does not have any units, so do not write molarity in there. We have 2 sig figs. This should be 2 sig figs, so I'm going to change it to 2 sig figs, and that's going to be 3.2 times 10 to the minus 7. And I should write Ksp equals. Okay, so that's my answer right there. Next one, at a certain temperature, 2.2 times 10 to the negative 4 grams of CuI will dissolve in a liter of water. Calculate the Ksp for CuI at this temperature and show all your logical steps. I know you probably want to be like using these things over here and saying, 1.3 times 10 to the negative 12, hey, that's the Ksp. But it says at a certain temperature. These Ksps are only true for 25 degrees. So what we're going to do is we're going to actually calculate this. Now, the thing is that when we are writing our Ksp expression, like that, so our Ksp for this particular one is going to be the concentration of Cu plus times I minus. Now, the concentration, this is going to be a 1 to 1 to 1 kind of ratio right here. And so, and all of these numbers need to be calculated in molarity. We're given grams per 1 liter of water. So what we're going to do is we're going to convert this 2.2 times 10 to the negative 4th grams into moles divided by 1 to give us molarity. And and then we can plug it into our KSP expression. So I'm going to go just do some regular stoichiometry. I'm just going to write my little test divider kind of thing right here and go 2.2 times 10 to the minus 4 grams of CuI. And so now I'm going to look up what is the molarity of CuI. Oh, sorry, not what the molarity of CuI is. What is the molar mass of CuI? So I'm going to use this thing way up here, and I find Cu is 63.5. So I'm just going to take a little thing up here. So CuI, this is 63.5. I is 126.9. 126.9. So the molar mass of these two things here, so I go 63.5 plus 126.9 equals 190.4. 190.4 grams. Grams is going to cancel out, and that's going to equal our moles. So it's going to be 2.2 times 10 to the minus 4 divided by 190.4 equals, and we get 1.155, and that's going to be moles. Now, since this question was very, very nice to us and said it's in 1 liter, I kind of made a little mistake right here. 1.155 times 10 to the negative, let's see, 1, 2, 3, 4, 5, 6, negative 6 moles. Got my scientific notation right there. So this is 1 liter right here. So I have to divide by 1 liter in order to get concentration. So this is actually going to be 1.155 times 10 to the negative 6. Divide this by 1, which just makes it turns into molarity. Now, since this is the molarity of CuI, it's a 1-to-1 ratio. It's also going to be the molarity of Cu and I. So KSP is simply going to equal 1.155 times 10 to the negative 6 times 1.155 times 10 to the negative 6. And I get, this is going to be again, this is going to be 2 sig figs. So this is all going to be 2 sig figs. I kept this as more sig figs and then just changed it at the very, very end. This is going to be 1.3 times 10 to the negative 12. And that's going to be our KSP. Now, CuI, and that's the number that we get right here. So it does happen to be that it's at 25 degrees Celsius. Okay. Last question. At a certain temperature, we have 0.0558 grams of strontium fluoride, and it dissolves in a half liter of water, or 500 mils. Calculate the KSP for SRF2 at this temperature. Show all your steps in a logical manner. Correct use of units and sig figs. Okay. So again, what we have right here, pretty much the exact same question, except the only little trick is that we now have SRF2 is going to go and turn into SR2 plus 2 F minuses. Okay, so it's no longer, unlike this question up here, which is a 1-to-1-to-1 ratio, this is a 1-to-1-to-2 ratio. So same thing, we're going to figure out what is the concentration of strontium fluoride. So we're going to go 0.0558 grams. We're going to convert this into moles. So 1 mole is equal to So I'm going to go way back up to my periodic table and look up where strontium is. So again, I'm just going to take a little bit of space from this here and go strontium is 87.6. Strontium is 87.6. Fluoride is 19, I believe. Yep. So fluoride is up here, is 19.0. There's two fluorides, so we have to have 19.0 twice. So now I'm going to calculate the molar mass of strontium fluoride, which is 87.6 plus 19 equals 125. Okay, grams cancel, and that's going to give us moles. So I'm going to go 0.0558 divided by 125.6, and that equals 4.44 times, and I ran out of room, of course, times 10 to the minus, let's see, 1, 2, 3, 4, negative 4, and that's moles. Okay. Now, here we have a half liter of water, or 0.5 liters of water, which is the same as 500 mils. So in order to convert into molarity, I'm going to go 4.44 times 10 to the negative 4 moles divided by our liters of water, which is going to be 0.5 liters of water. And that's going to give us our molarity. So divided by 0.5 equals, and that's going to be 8.885. Negative 4, and maybe I can squeeze it in, molarity. Okay, so bringing this number that we just found out, what is the concentration of this stuff, that is going to make this stuff right here 8.89 times 10 to the negative 4. Now, since this is a 1 to 2 ratio, that this will also be 8.89 times 10 to the negative 4. But this one will be twice as much, so times 2 equals, and this will be 1.77 times 10 to the negative 1, 2, 3, negative 3. Okay. Now, our KSP expression is going to be our product, so it's going to be concentration of SR, 2 plus, times our concentration of F minus, 2 there, so we have to square it. Okay. And so therefore our KSP equals, what we got here, 8.89 times 10 to the minus 4 times 1.77 times 10 to the negative 3 squared. Okay, I know for some people it seems a little bit weird that we're multiplying it by 2 and we're squaring it. Multiplying by 2 makes sure that we're following the ratio. The squaring process makes sure that we're plugging in and using our KSP formula correctly. That's why they're related and they look very similar, but essentially that we have to make sure that we times it by 2 when we find this calculation, and we also have to later on square this number. Just realizing, look at all this extra room I didn't know that I had. Anyways, I'm going to plug this into my calculator to find out what my KSP is. So we're going to square this number. Square equals, and then times 0.89 times 10 to the minus 4, I believe. Yep. Equals. And my calculator isn't the best one in the world. It doesn't really like showing me all these numbers. It only gives me one sig fig here. So it just says 3.0 times 10 to the minus, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the minus 9. Okay. Your answer could definitely be different if you had a calculator that gives more than 10 digits. Mine only does. I need to upgrade my calculator game here. Anyways, so here's this. I will post this answer sheet on our Microsoft Teams in case you just want the straight up answer. But if you want to see me how I did this, then I'll post this as a YouTube video as well, so you can see me talk through it and all that kind of stuff. Okay.